So our next speaker is Phil Muirhead, and he'll tell us about the intensification and saturation of M-dwarf absorption lines with Rossby number. So please, Phil, go ahead.
Great, thank you, Victor. Can you hear me? I think
yes, we can.
Excellent, great. Okay, it's nice to see some of you. In my talk, I'm going to talk about a project I worked on while I was at Exostar a year ago with fellow Exostar member Elizabeth Newton and also some other collaborators, including a former PhD student of mine, Mark Bayet, who's gone off to Lockheed Martin now. The title of my talk, Intensification Saturation of M-dwarf Absorption Lines with Rossby number, and we have a paper that was published earlier this year, and there's the archive number if you're interested. So the context for this work involves this feature that is seen for stars with convective envelopes, FGK stars and M-dwarf stars, wherein at lower and lower Rossby number, activity indicators appear to saturate. And this has been studied for a long time, so I'm showing 3 plots here from papers across multiple decades, going back to the 1980s, by Noyes et al., where I hope you can see my mouse here, where they show that for decreasing Rossby number in the star, where the Rossby number is defined as the rotation period of the star divided by the convective turnover time, which of course is something you have to assume. You have to use a model to assume what that is. It's a very difficult thing to directly measure. But you can calculate this Rossby number for stars, and they see this effect where this particular activity indicator, which is based on calcium H and K lines, appears to start to saturate at lower and lower Rossby number. This study by Noyes et al. Was done with neighborhood FGK stars using V sin I as a proxy for rotation. Then later we have some work by Soderblom and collaborators in the 90s where they see the same effect, but they were studying FGK stars in the Pleiades. So these stars, because they're young, they're actually rotating faster, you can get to even lower Rossby numbers. And here you clearly see the saturation effect. At these low Rossby numbers, you're getting a saturation in this activity indicator. And in this case, the activity indicator is H alpha. I apologize for the backwards, for these appearing odd. I had to flip the plot to match it to the other one, so I just flipped this plot. If you go to their paper, you can see it flipped the other way. And then over here, we have some more recent results by Wright and collaborators. Let me move my Zoom window over so I can see this. Showing the same thing, we go to lower and lower Rossby numbers, and we see this saturation of X-rays. In this case, the activity indicator is coming from the corona, which produces the X-rays. In the case of this very nice paper from 2011, Wright et al. Basically grabbed any star they could that had X-rays and a photometric rotation period with convective envelopes. So that's why we have so many objects here, and you very clearly see this saturation effect. I became interested in this. Ooh, what's going on here? Oh, there we go. Because I'm really interested in what's the mechanism, what's the fundamental mechanism that's causing this saturation that you see. There have been a few proposed over the years. So one of the original proposals was this idea of coronal stripping. So the idea here is that as you go to lower and lower Rossby numbers, your rotation period is getting lower and lower, spinning faster and faster relative to your convective turnover time. So your magnetic fields are getting stronger, which should result in a hotter chromosphere, or in this case corona, a hotter corona. But you're also going to have centrifugal forces throwing away a lot of those ions and hydrogen. And so you actually have an increase in temperature, but a decrease in density. And so that could be causing this apparent saturation. Now, this particular theory has gone out of favor for explaining the, the saturation here, but it has come into favor for explaining a supersaturation that has been seen in some studies of X-rays. Other mechanisms include maybe there's some intrinsic limit to where you can put spots on a stellar photosphere. Maybe the photosphere can only sustain a certain spot filling fraction. And then another proposed mechanism is that maybe the dynamo itself, the mechanism that generates the magnetic fields in the first place, itself could be saturating. And so over here, I've made a very dumb PowerPoint cartoon. I probably could have made something fancier, but I guess I was lazy. trying to capture the fact that in these different proposed scenarios, they're localizing the mechanism to particular regions in the star. So coronal stripping would localize the mechanism, of course, to the corona. A maximum spot filling factor would localize it to the photosphere, and saturation of the dynamo itself would localize the mechanism to the dynamo. And there is evidence actually supporting and disfavoring these various theories. I don't quite have time to go through all of it, but I can talk a little bit about it. But I became interested in this because M-dwarfs are a wonderful opportunity to study the saturation effect, and that's because M-dwarfs have very long spin-down timescales. This is a figure showing the saturation effect with H-alpha on the y-axis, Rossby number on the x-axis, and this is not by me, this is by my collaborator Elizabeth Newton from a previous paper. M-dwarfs are great because they have these long spin-down timescales. It takes billions of years for them to spin down and go down into this unsaturated regime, which means you can grab all the nearby ones, the bright ones, and throw them on a plot like this and really investigate them in detail. Whereas for the FGK stars, you have to go to clusters. They're further away. They're fainter. So M-dwarfs provide a really nice opportunity to investigate this. And in 2009, there was a nice paper by Reiners, Basri, and Browning. Matt Browning, of course, participated in Exostar, so we had a number of nice discussions a year ago where they derived the magnetic field in the photosphere of the spots using the Zmon effect of iron hydride lines for a number of M-dwarfs, and they also see the saturation effect in the magnetic field versus Rossby number. And this is really the first evidence that the saturation mechanism is at or beneath the stellar photosphere. So this actually disfavors a stripping mechanism for creating that flat line. Now, it doesn't mean the stripping mechanism can't cause the supersaturation, which I'm not going to talk about. So there could still be coronal stripping, but this is evidence that the fundamental mechanism is either a spot filling factor, so the second one, or the dynamo itself. So I kind of fell into this because I've been studying M-dwarf stars in Y-band, which is a really wonderful spectroscopic region to study M-dwarfs because there are no telluric lines, believe it or not. Great place to go look in the infrared at M-dwarfs. And you have all of these very nice lines. You, of course, have the iron hydride band. This is actually the same iron hydride band that was used by Reiners et al. In 2009. But you also have these very deep lines here from neutral titanium and neutral calcium. I originally set out with my former PhD student to try to use this to measure ages of M-dwarfs because titanium is actually an indicator of alpha enhancement. So this could be used to measure ages. It turns out it didn't work very well in this case. It's worked for other objects, but it didn't work well for our rapid rotators because of this effect of Zmon enhancement, which I'm going to talk about. So we set out to acquire Y-band spectra for a number of M-dwarfs with a variety of Rossby numbers here now on the y-axis and a variety of masses. We have a sample. We developed a sample based basically on Elizabeth Newton's thesis work, which is shown as unfilled circles. We observed the filled circles, and so we got a nice wide range of Rossby numbers at any given mass, and then we supplemented it with public spectra, publicly available spectra from the Carmenez survey. So thank you so much to the Carmenez team for publishing their spectra, making it publicly available so we could play with it. And so we basically have dozens and dozens of M-dwarfs spanning a range of masses and Rossby numbers with observations in Y-band with these very deep titanium lines. And this is just showing how complicated spectral analysis is for M-dwarf stars. We don't have a very clear continuum. We instead have a pseudo continuum upon which we measure the equivalent widths of these lines. But the description of how we measure the equivalent widths of those titanium lines is described in a paper by Bayet et al. In 2017 and also his thesis. All of our targets have C over V sin I's less than the resolution of near spec, so the V sin I broadening does not actually affect our measurements. And we saw something very interesting when we did this. Again, we originally did this to measure ages, but we saw something else. We saw the very same saturation effect that's seen in the activity indicators, but instead of H-alpha, calcium H and K, or X-rays, or B fields directly derived from iron hydride, we just see the equivalent widths themselves appear to saturate with decreasing Rossby number. So the very same kind of pattern where as you go down in Rossby number, you reach this 10 to the minus 1 Rossby number, and then it saturates. So we're actually seeing saturation in the absorption lines. And we attribute this to this really interesting effect, which I was unfamiliar with, but I've become very familiar with it, thanks partly to all of our great discussions during Exostar, called Zmon Enhancement. Of course, we all learn about Zmon broadening, the broadening of the line, but this is a different effect. It's related, wherein you actually change the curve of growth for an absorption line by introducing Zmon broadening. So this is a photograph from a very nice textbook on stellar astrophysics by Hansen, Qualler, and Trimble showing the famous curve of growth. As you increase either number density or oscillator strength, you're going to see an increase in the equivalent width until the line is saturated, and then you have the dampening wings come in. So this is sort of first-year grad school stuff. But the thing is, if you split or broaden an absorption line, you actually extend the linear regime of the curve of growth, and so your equivalent widths become larger just by adding magnetic fields, which is really confusing. I think of equivalent widths are not supposed to be affected by broadening. That's the whole point. That's why we use it. But if they're broadened by the Zmon effect, you can actually increase the equivalent width because of this change in the curve of growth. And that's, in fact, exactly what we see if I plot equivalent width for our titanium lines versus the oscillator strength for the lines colored by Rossby number. We actually see the saturated regime. These are all in the saturated regime, which we can calculate. They increase in equivalent width versus Rossby number. So this region right here is actually increasing. So that's what we attribute it to. So the lines are saturating in absorption with Rossby number. It's interesting that the line strength is not mass dependent. It's only Rossby dependent. So here, all of these colors are actually go by the mass of the star, and it's just a mix. This result is purely empirical. We have not modeled B fields at all. We're just looking at equivalent width. And this is further evidence, along with Reiners et al. 2009, that the mechanism for saturation is at or beneath the stellar photosphere. It is not the mechanism that's causing this saturating effect here and here is not inherent to the chromosphere and corona. It's actually in the photosphere deeper. So that really suggests that we're either dealing with a maximum spot filling factor or saturation of the dynamo itself. But unlike Reiners et al., we did not do any modeling, and we used photometric rotation periods, not V sin I. So it's really enhancing. I feel like it's enhancing that result. So I have no time. So I just have 2 slides here. Next steps, we have some recent efforts funded by the NSF. We'd like to apply spectral retrieval methods used on L&T dwarfs to M-dwarfs. This is something I'm doing with Jonathan Fortney and Mike Line. And then there's another program to add magnetic fields to atmospheric models to model apogee data. This is something I'm working on with Katja, who's the PI, and Vern Smith. Both are going to tell us more about the saturation effects in the photosphere. But they don't really tell us how we can test whether the dynamo saturates. And so that's something I'm interested in. Maybe we can talk about it in the discussion section. What observational tests can we do to test whether the dynamo itself, that is, there's some sort of quenching going on in the dynamo? I don't know how to do it, so maybe someone else here does. Just some things I learned from Exostar. Elizabeth Newton was super helpful in understanding the state of the field and is a collaborator on this. Svetlana Berdujina was very helpful with modeling. We skipped modeling in this result, but we'll hopefully get back to it. And Jim Fuller had a really interesting comment about how the increase in opacity from magnetic fields would affect evolutionary models, because you're increasing the opacity if you increase the equivalent widths. Could that actually change the evolutionary models for M-dwarfs? So that's something interesting we could also talk about. I don't know the answer, but I really like that idea, so maybe I'll get to it. And I just want to thank the Exostar organizers, and if you're interested in this, we have a paper, and that's our archive number. So thank you very much.
Thank you very much, Phil. Just a short notice for people writing on the chat. Please make sure that you send your answers to all panelists and at least, otherwise I think they only go to the panelists. So Pierre and Max, I think you send your answers only to the panelists. Okay, questions for Phil, comments. We have a couple of minutes for questions from the audience. Maybe what people think, I would like to follow up a bit, Phil, on what you said about the opacities at the very end. Maybe I was just curious about that. When you speak about an increase in the opacities, how much? Yeah, it was on your last slide.
Yeah. So please ask your question. Sorry.
Yeah. No, I mean, this. How much are we speaking? Is it and motivated by what? Is it the solar abundances question that motivates the increase in the opacities? Is that the level that we're speaking about?
Yeah. So when Jim asked that question, I'll admit my first thought was like, well, okay, if you increase the opacities of these handful of titanium lines, you're not going to change like the Roslin mean opacity of the photosphere. You know, it's just a handful of lines. But suppose by adding magnetic fields, you Zmon broaden something like water vapor lines. Now, I haven't thought about this. I haven't done any experiments on this, but let's suppose you broaden the water vapor lines and increased and basically lifted this saturated regime for all of the water vapor lines in a star. Well, now you could conceivably dramatically change the Roslin mean opacity in the photosphere of the M-dwarf. And that, when you paste that new atmosphere on an evolutionary model like MESA, you have to turn up the Roslin mean opacity, and boom, your star is going to get bigger. Well, when you evolve it, your star is going to get bigger. And so I think our conversation was saying maybe this is a potential way to explain the radius discrepancy that's seen in M-dwarf stars. That was the idea. But I think it's purely a discussion. I have not done any work on it.
And I'm just going to follow up with a question on the chat from Dawson. So he says that some M-dwarfs appears to not exhibit radius inflation with rotation/activity. Is there evidence for two populations of M-dwarfs, perhaps in terms of field properties, in any of the rotation-activity relations you have studied?
So I heard some of that. Let me pull up the chat here so I can see it. So yes, some M-dwarfs do not exhibit radius inflation. Well, yeah, so this has been an ongoing question. Is there a inflation and rotation radius relationship? And I have yet to see really definitive results suggesting that as you increase rotation and you increase magnetic field, does that increase the inflation? Although people have studied it. Adam Krauss had a paper from, I don't know, a decade ago, where it sort of hinted that there might be that relationship. Is there evidence for two populations? I have not, in my work, I have not seen an evidence for two populations. However, there is some very nice work by a member of the Carmenez team, who I didn't have time to talk about his work, is in his collaborative work. Dennis Shuliak and collaborators do have some investigations where they suggest there are these two field structures that appear in rapidly rotating M-dwarfs. And they actually suggest there are two populations. So I would suggest checking out Shuliak et al. 2018 and 2017, I think, where they actually do suggest there are different populations of field structures on M-dwarfs.
Perfect. Thanks so much, Phil. Another virtual clap for you. Thank you so much for this very excellent presentation.
Sure. Thank you.
And